So I'm Baptiste Poirier from Cerema in France, and I was PhD student, and I did my PhD in l'OSCI in Université Savoie-Mont-Blanc in Chambéry, and the work I will present today is based on a paper I present in last AIVC conference and also on my PhD work. And we had a performance-based approach for smart ventilation, and today I will make a focus on ranking and method for ranking the performance of the systems. A little bit of context of energy and building and ventilation. So the building sector is part of total energy consumption in Europe, and in focus of in the French context it as part of carbon emission. And in other side, the ventilation and indoor quality in building is important, as we spend between 60 to 90% time of our time in building, and it has a cost for health because of bad air in indoor quality. And so the ventilation is as a cross section of energy and EAQ aspect in building, and but today with increasing the heat loss and air tightness of building, there is a need of air renewal, and that question how to keep good indoor air quality without increasing the amount of energy lost due to air ventilation. And the question today was how to aggregate performance indicator and balance EAQ and energy performance for assessment, and to provide a robust ranking of ventilation system. So for this study, we performed a simulation on a French low energy housing case study with it's a 2-floor housing with 5 occupants. So 2 occupants in the master bedroom and 1 occupant in each other bedroom. And we make simulation and modeling a balanced ventilation system and exhaust only ventilation system with exhaust in kitchen and bathroom, and supply in the living room and bedroom when it's balanced, and air inlet at the windows when it's exhaust only ventilation system. Then we make modeling on 5 ventilation systems from constant to smart ventilation system. So the reference system first is the constant ventilation system with a cooking boost, exhaust cooking boost during cooking event at lunchtime and during dinner, and both exhaust only and it balance with heat recovery. Then a second system with its exhaust only ventilation system with humidity control in bathroom and in kitchen. So there is a range of control based on depending of the humidity, relative humidity level, and when the humidity level increase during shower event or cooking event, for example, there is a higher airflow, and the cooking boost is kept also with this strategy. And lastly, we make modeling of more smart and advanced ventilation control strategy based on humidity and CO2 level, and at the room-based and at the room level scale for control. That means depending of the CO2 level in the bedroom and in the living room, and or the humidity level in other room, there is a exhaust airflow demand which is calculated and then applied on the exhaust airflow. So, for example, we can see here that during night, when people are sleeping, there is CO2 accumulation in bedroom, and we have higher airflow when there is people during night and a lot of CO2. And during the day, when there is nobody in the building, there is low airflow. and we keep also the high airflow during cooking events. So the approach was to perform design option calculation by we make simulation for sensitivity analysis work, and we perform reference scenario with low reference and high emission scenario for CO2, formaldehyde, PM2.5, and humidity pollutant. And also we make change in the range of variation of the airflow of total exhaust airflow with lower total exhaust airflow or higher airflow. And we perform a total of 500 simulations for each motivation system design, and that made a total of 2,500 simulation. And we perform airflow simulation with Quantum. And with this simulation, we calculate 5 indoor air quality performance indicator and 1 energy indicator, which is based on CO2, formaldehyde, PM2.5, and humidity for air quality. We calculate the exposure, the total exposure of the occupant for formaldehyde and PM2.5 and CO2 exposure over 100 ppm. And for humidity, we had two type of indicator. One of the time spent by over 70% of relative humidity, and the time spent by the occupant out the range of 30 and 70% of humidity. One more for mold growth risk, and the other more for the comfort and health aspects for the occupant, and then the energy one. So all these indicators were then normalized by EIQ acceptable threshold. For each indicator, we define acceptable level, and we normalize the result. That means if the indicator result is over 1, that means it's over the acceptable threshold, and the performance is worse than we can accept. And if the result is lower than 1, that means the EIQ aspect start to be acceptable. And but here is this graph shows the distribution of the result in box plot for each system, for each indicator, and over the 500 simulation. And it's a bit hard to make a lot of wrong the system, but if we can look that the room-based system with its recovery is in most time lower than the other system in results. So we can say it's for this EIQ aspect the first system. Then we have the green system, which also room-based with exhaust only, is in most time lower than the other. And then we have the constant heat recovery system and the exhaust only humidity control and constant exhaust only. So for EIQ, it's a bit possible to see there is some system which have a more acceptable performance than the other, or more condensed. Now we perform also, we calculate, as we have only airflow simulation, we don't have energy simulation. We propose a really simple energy performance indicator, which is based on the heat loss from exhaust airflow. It's the volume of exhaust airflow multiplied by the heat coefficient and the delta temperature from outside to inside, that give you an idea of the amount of heat loss from the airflow renewable. And we apply 80% heat recovery efficiency coefficient for the two heat recovery system. So that's why the these two one are really lower than the exhaust only ventilation system. But we can see that humidity control system has a better performance regarding energy than the constant exhaust and the smart room base. So because of the heat recovery, the two heat recovery systems are the two best, are first in the ranking. And then we can give a ranking. But now the question was how to choose the most relevant from a global performance overview because of between the EAQ performance aspect and the energy performance aspect. It's a bit more tricky, and so to answer that, we propose a ranking method to aggregate the performance and in a simplified approach in three key steps. With the first step is the design option performance, so I present you the result. Then we propose to aggregate the result of all the simulation and all the for each simulation of all the to aggregate the EAQ and the energy aspect with a simply additive weight method I will present you, and then to integrate all the indicator from all the simulation, we propose a robust calculation and ranking method to calculate one design score by each system and to help for decision making. So the second step to aggregate the EAQ and energy indicator to go from 6 indicator in one aggregated value for each simulation. We try three distribution of weighting. The first one is EAQ only. That means energy aspect have 0 weight and don't count in the total aggregated indicator. And then evenly distribute weighting. So all the indicators have the same weight. That means energy represent only 17% of the weight, and there is 84% weight for EAQ aspect. And then we try to propose the EAQ E star another distribution, which is more balanced and to have 50% of energy of weight in energy and 50% of weight in EAQ. So here is the box plot of the aggregated indicator. So it's only one indicator for the 500 simulation. And so regarding EAQ aspect, only we observe almost the same ranking as we observed previously. And when we start to integrate the energy performance, the two heat recovery systems start to be lower as they have better energy performance than the two exhaust only systems. So the comparison should be between heat recovery or between exhaust only. And lastly, if we give even more weight for energy on energy, the gap between heat recovery and non-heat recovery system is higher. And then we try to integrate the result of all the simulation in only one score, it's the design score. And we propose to use the min-max regret method. We in the paper and in my PhD, we test 5 different methods, and we keep this one because it was one of the most conservative approach to keep balance the result between system and to keep it yes balanced, because other aggregation methods sometimes increase artificially the gap between the results, and this one was one of the most conservative method. So now I propose you to only focus on the design score result with the two EAQ and energy EAQ energy aggregation. And so if we give the same weight of on all the indicator, we have a final ranking, but the room-based heat recovery system is always first. Then the constant airflow with heat recovery also always second because of the good heat recovery performance. And but there is a change between the relative humidity control and room-based system with constant airflow, depending which weight we give on the energy aspect. And indeed, for the room-based system with exhaust only, there is in average higher airflow that increase the energy loss, and in average for the design score that give worse performance than the relative humidity control system. So to conclude, and the learning of this study that with evenly distributed EAQ energy distribution, we can have a conservative approach where with the EAQ could be the priority for decision in the decision making process. And if we increase the weight of energy aspect for decision making, there is a equal proportion between EAQ and energy. And this study highlights that the design score could help to highlight the difference between several ventilation system and strategy, and to help in order to rank them, and including the uncertainty of several simulation aspects. So with work there is a lot of perspective on this aspect, and that question how to weight energy and EAQ in such performance-based approach, and to rank the performance of ventilation system. Thank you for your attention, and I will let Samuel Caillou continue for the next presentation.